Hadley circulation has fascinated human beings for a long time. So if we go back to the Halley's time, the same Halley of the Halley's comet, he described the Tradewind Theory as warm air being more rarefied or buoyant, as the idea is that Earth is going from west to east, which means Sun is going from east to west. So where the Sun is, there is a heating, and there is a nighttime side of the Earth where there is a cooling and larger pressure, greater pressure. So then you have a pressure gradient that can drive westward trade winds. Obviously didn't say much about what happens on the other side. Why isn't there westerly flow from the other side of the sphere? But nonetheless, the idea was that there must be rising air over the sunlit patch of the Earth, which is warm and low pressure, rising air. Likewise, over the dark and cold side, the air must be ponderous or heavy and sink downward. With such disequilibrium, horizontal air currents must be rushing between the dark side and the daytime side, with the patch of solar heating ever circling westward around the planet. We have easterly trade winds. This is from Chris Karnauskas, our dear friend from CU Boulder, writing an essay on Halley's Tradewind Theory, and he argued that this is true in some cases, which you can read up his essay for why this could be. This was considered not so wrong at the time or even now. I forgot the details, but you can look it up. But even before this, Galileo had basically said that as Earth rotates around the equator, you have a larger radius, so within 24 hours you have to cover much more distance, so the linear tangential velocity is much greater at the equator than off the equator. So the air is just not able to keep up with the planet. So if you're sitting on the planet, then it feels like the winds are coming from the east towards the west, whereas if you go off the equator, then the Earth is smaller and moving slower in 24 hours in terms of tangential velocity, so the winds are going faster, so you would get westerly winds, which seems fairly simple, but obviously they missed the point about the rotational effects that Halley had become aware of. Copernicus also tried to explain the ocean currents with the same idea. Later on, Hadley came along in 1735. He actually wrote a little paper which has no figures, where he tried to explain that the heating in the deep tropics causes rising motion, and the cold polar latitudes have a sinking motion. And if you consider again the rotational effects and angular momentum, so if you pick up slower eastward velocities of the Earth and try to go towards the south, you're going to be going slower than the Earth, so you're going to fall behind this way. Whereas if you are coming from this latitude towards the equator, the Earth is moving faster, so you're going to be tilted this way. So the Coriolis effect formalism only came out almost a century later by Gustave Gaspard Coriolis from France, but Hadley had the proper idea of why you would end up with these northeast and southeast trade winds if you consider angular momentum and this radiation driven circulation. Okay, obviously he didn't realize that if you raise a air parcel from here with this angular momentum and try to move it towards the poles, you cannot have a circulation going all the way to the pole, because as we will see, the angular momentum cannot be conserved and the system breaks down somewhere along the way, which is related to actually the Hadley termination that we're talking about. So this figure was constructed by David Babb based on on Hadley's paper, but obviously the cell is named after him because he basically got the essential crux of the matter in terms of radiation-driven meridional circulation and angular momentum conservation leading to trade winds. So that leads us to axisymmetric meridional circulation models. We will look at zonally average perspective of meridional circulation. Even though the zonal asymmetries are fairly significant, as I said, radiational heating and cooling and eddies from the basic state instabilities in the longitudinal direction, as well as the interaction of the, let's say, trade winds with the heating and orography is going to create plenty of zonal asymmetries, which actually you have already seen as well in terms of the heating and the Walker cell of the Pacific Atlantic Oceans and the piece over the Indian Ocean and so on. So the heating in the longitudinal direction, as we can see here for different seasons, includes the latent and sensible heats along the equator and along 25 north. So we have not much of seasonality at the equator. Obviously tropics have not much of a season, whereas if you go to 25 north you have a very strong seasonality because of the tilt of the earth and the sun moving back and forth. So if you look at net radiative forcing, a similar story evolves. Of course there are impacts of land and ocean that matter as well. So these longitudinal heating gradients do matter, as we will see later on in a three-dimensional circulation. But in a zonally symmetric case, we will ignore those, and I will come to the equations in the next podcast and leave this short podcast here, just reminding ourselves that the Hadley cell theory and relation to the trade winds have been going on for several centuries. And remember, during the time of Galileo, Copernicus, Halley and Hadley, there wasn't that much information about the upper levels, and there were lots of information from the ships about the trade winds. And as we mentioned before, there is a debate about whether trade winds are related to actual ship trades or whether it is related to a sailing terminology and so on, but we will leave it as it is and then come back to the equations that govern this zonal mean meridional circulation that we are interested in this chapter in the context of tropical impacts on the extratropics.